Hello everyone. In this video, I will be covering the design of a digital ecosystem using difference equation concepts from the Z transform. Z transform in itself will not be useful in this matter, but difference equation will 100% will. Let's now di- discuss what an ecosystem really is. Suppose that our system or our algorithm, um, what it does is this is the speaker and this is the reading. So this is the recording that I will record in some time. It will play that as it is to the speaker. But now what I want to do is that I want to suppose this is the recording starting from zero. What I want to do is I want to delay it by some let's say 500 milliseconds speaking realistically, and then add that back to this. So we'll get a form of echo signal. So a difference equation thus becomes x of n minus n, where n is the delay, talking about samples, that is in n. The unit is n. And one more thing is that after a delay, I don't want that full amplitude to come. Obviously, echo comes after some attenuation. So what better than to attenuate with by multiplying it with zero point 0.5. So it will be the half. And this is really the basis of our ecosystem. If this is ready, then I think 50% of the work is already done. Now, now let's convert this equation into some real form that we can use in our Python program that we'll be coding. So this is 0.5, the attenuation factor, x of n minus. Now let's calculate the n value. How many samples should we really put to 20,000, 10,000, 5,000? For that matter, we must understand what n really means in this context. So here n is again is just samples arranged one by one. They aren't time stamped. These are not time stamped. They are continuous. We must know about what they are sampled at, the rate of sampling. So to extend this point, a normal audio signal is sampled at around 44.1 kilohertz or 44.8 kilohertz. And let's determine what hours is sampled at. So coming to system properties here, this is my mic, and we can see that I have set it to 44100 hertz. Coming back to our canvas, 441 kilohertz means that per 1 second of time unit, there will be about 44,000 unit, stuff like that. So if you wanted to seek, let's say 1 second ahead of time, you would do n plus or minus, I think, 44,000. This gives us an idea of how much we need to delay. Now the question comes, how many seconds to delay? So let us say that we want to delay our voice, whatever. Let's say if I say hello or if I say check, it should come after 500 millisecond, half a second. So what does that mean? It means that my n value must be half of this, since in 1 second it has these many values. So if I'm not wrong, this is the value with which I need to delay my input signal and add it back. Sorry, so this is nothing but the very equation that I'll be using in Python in order to generate an echo. So yeah, Unfortunately, the audio was cut out for the entire clip of the recording, uh, wherein I was typing out all this. But to explain it simply, these are the libraries that I used. First is for processing creating empty arrays, for adding many empty entries to the input signal. I'll talk about this later. So NumPy for that and scipher.io for reading my recording. And now the first line, this is the read function. It returns the sampling rate and the list of samples. Next is the attenuation factor 0.5. Then after that, the delay. So here the delay of this much was kept mainly because as I had calculated, 4110 whatever divided by 2 is that much, and precisely 500 is it. Then we are creating an array. We're kind of reassigning it. Herein I'm converting 16-bit PCM format to 0 to 1 float values. This will be very important for preventing clipping issues as I do the echo addition. Next, I'm padding, or rather, I'm after the end of let's say a 9-second clip, right? I'm adding more additional 500 millisecond. Or yeah, and the reason for that is because for n equals to 0, there is essentially no when we do n 0 minus something, Python kinda goes reverse and gets the samples from there, but we don't want that. Normally what happens is that we assume n minus 1, 2, 3, whatever is 0. So that's what this padding function is doing. It's for mimicking that behavior. Next, getting this output array ready with length plus delay. Delay is for accommodating, it's my personal choice, of course, where I'm accommodating 500 milliseconds additionally so that I can get to hear the last voices delay echo as well. Next, this is the main operation. In this for loop, what we're doing is that difference equation operation only, nothing else. Next, we're normalizing it. What is being done here is that this is the maximum value of whatever y values there are, and dividing it by each and every sum. So what that is doing is, if there is any clipping obtained by the echo, so those things will be sort of companding. I think so. Companding, the concept of companding is here. Not really sure of this, since the code was made with the help of this chat. Next on, we have it converts back floats values to integer values, 16-bit PCM, of course. And finally, it is written back to echo.wave. This is the outcome of this program, actually. This is the original recording. I'll play it again. This is what I want to echo using the transform or rather difference equations. Let's see how this goes on. And with a delay of around, how many is this? Let's say 440 milliseconds or something. So this will be. This is what I want to echo use transform or rather difference equations. Let's see how this goes on. And if we modify this to 2, so there will be a delay of 500 milliseconds only. So recreating the type it again. And yeah, we have to open that. Let's see. This is what I want to echo using transform or rather difference equations. Let's see how this goes on. And that's pretty cool, isn't it? So this is the essence of difference equations applied for a digital ecosystem. Thanks for watching.